I recently worked on a project where my responsibility was to implement a scale backend for a full stack application that aimed to replicate an Epic Game Store product page. The application allowed clients to request information about video games, including name, rating, video trailer, description, genre, and the product information like the developer, publisher, release date, and platform. To implement the scale backend, I utilized various technologies including Node, Express, Postgres database, K6, Faker.js, Docker, Redis, and DigitalOcean. Within the Postgres database, I incorporated 10,000 records of fake data generated using Faker.js, and I did this to simulate the stock of video games and their corresponding product information that would be available to customers. One of the biggest challenges I encountered during the implementation of the scale backend was refactoring the project's backend to conduct load tests and utilize DigitalOcean. The project I inherited was originally developed with Supabase, and I didn't have the rights to seed this database with thousands of records. To overcome this issue, I migrated the tables along with the seeded data from Supabase to a Postgres image within the Docker container. I accomplished this by referencing the table definitions and seeded data from the Supabase database and created SQL files within the project's directory. And then I created a Docker container containing a Postgres image using Docker Compose that I then initialized with the newly created SQL files. Another obstacle I faced was during the base load tests using K6 to send metrics to Grafana. Simulating 5,000 concurrent users exceeded the expected push interval configuration for InfluxDB, resulting in a cascade of failed requests and occasional timeout errors during the load tests. To address this, I optimized my load test script to simulate only 100 virtual users, reducing the amount of generated data and the number of requests made to ensure data can be processed and sent within the configured interval. After overcoming these challenges, I established an excellent baseline for my application's performance, providing a starting point for further optimization. Initially, the server and database architecture for the application followed a distributed monolith approach, and to enhance scalability and performance, I implemented several optimizations. First, I containerized the Express servers using Docker Compose to ensure consistent deployment and ease of scalability. To host the Express container, I set up a DigitalOcean droplet. I also created a separate DigitalOcean droplet with a Postgres database cluster where I migrated the tables and seeded the database with 10,000 records of fake data using Faker.js. To compare the metrics of the application's original architecture, I consolidated the isolated Express servers into a single file that I then pushed into a Docker container. This container was then deployed to DigitalOcean to simplify the infrastructure and reduce overhead. I also Dockerized a Redis server and deployed it to its own DigitalOcean droplet. Redis caching was utilized to enhance caching mechanisms and improve the overall performance of the application. During the load tests, I conducted both base and vertically scaled configurations. The base test consisted of one virtual machine with 2 virtual CPUs and 2 GB of Intel RAM. The test had a duration of 10 minutes with 100 virtual users. It ramped up from 0 to 100 virtual users over 2 minutes, stayed at 100 virtual users for 5 minutes, and then ramped down over 3 minutes until reaching 0 virtual users. The vertically scaled tests utilized one virtual machine with 4 virtual CPUs and 8 GB of Intel RAM, and it maintained the same durations and ramp up, ramp down configurations as the base test. When collecting the test data, the metrics I focused on were response time, throughput, and error rate. These metrics provide valuable insights into the application's performance bottlenecks, scalability, and stability. The 3 architectures measured was the original distributed monolith architecture, a single server monolith architecture, and the single server architecture implemented with Redis. The findings for average response time indicated that the distributed monolith architecture exhibited higher response times compared to the single server monolith. However, introducing Redis caching to the single server monolith significantly improved response times. In terms of average throughput, the single server monolith with Redis achieved the highest throughput, indicating effective utilization of caching mechanisms. On the other hand, the distributed monolith had the lowest throughput. Regarding the error rate, it remained relatively consistent across different architectures and scaling configurations. The single server monolith with Redis exhibited the highest error rate, and this is likely due to the significantly higher request load per second compared to the other architectures. Overall, the introduction of Redis caching improved the application's performance, resulting in lower response times and higher throughput. The distributed monolith architecture faced challenges in achieving optimal response times and throughput compared to the single server monolith. To further optimize the application, potential bottlenecks include identifying and optimizing resource-intensive components in the distributed monolith architecture, exploring horizontal scaling options to distribute the load more effectively, and conducting further analysis to ensure the factors contributing to the higher error rates.